Good morning, everybody. Today we'll start our lecture, the first lecture, building a multiple sequence alignment. In this, by the end of this lecture, you should understand why multiple sequence alignment is useful for biologists, how identify situation where multiple sequence alignment don't help, and the main criteria for building a multiple sequence alignment, main application for multiple sequence alignment, what kind of sequence you are looking for, tips for naming sequences, and tips for difficult multiple sequence alignment to interpret. And of course, by the end of this lecture also you will know how to compare sequences that cannot be aligned. The first thing is how to know how to gather sequences, and we will have a lecture about that, maybe the next one. And also we'll see some differences in some very famous multiple sequence alignment programs like coupled, Clustal W or Clustal Omega, Muscle, and TCAF. They just for examples, and these are four famous programs that everybody uses it, and we'll see the difference between each one of them and how and when we will use each one of them. Also, we'll learn in the coming lectures creating and comparing multiple sequence alignment with comparing sequences that you cannot align, as we mentioned before. As a biologist, you will have this multiple sequence alignment as a very important tool, something like a Swiss knife for MacGyver in the movies. He usually uses Swiss knife to make important things. So for biologists, multiple sequence alignment is very important to interpret a lot of data and extract a lot of information from your sequences. But actually it's not a science, it's an art, and you have to use all the information you have, all the knowledge you have in biology and bioinformatics to interpret your data and extract a lot of information from your multiple sequence alignment. Before we start, we have to identify some situation where multiple sequence alignment cannot help. In this situation, for example, assembling sequence, for example, in a sequencing project, you would like to assemble some sequences, multiple sequence alignment would not help you. Also, to turn EST cluster into a gene, or to find, to make a multiple sequence alignment with a gene that have no homologue in the database. This is also very difficult to use to make multiple sequence alignment. So in the last case, where you cannot find homologue for your sequence, in this case you can of course use some functional criteria and conducting pattern search using some other programs that we will see some examples in the coming slides. Anyway, first, if you would like to build a multiple sequence alignment and to get information from it, so in this case you would like to know how to gather your sequences in the right way, how to compute your sequence in the right way. Also, evaluation is very important, evaluation of the quality of the alignment and of the interpreting of your alignment. Interpretation is a very important step, and in this step you have to use all your information, all your background in biology or even computer science to get all the data you'd like to interpret. And number 5 is to keep the sequences for further analysis in the future. And there is very, very important step, because you may use other programs to confirm your first result or something else. So that's why this step is very important. We will start with gathering your sequence, and we finish by keeping the sequence that you have already gathered. So what are you looking for the multiple sequence alignment? Of course, there is four major criteria, and these four major criteria start with structure similarity. And in this case, we are looking for a structure superposition. This means that we would like to see the amino acids or nucleotides in the same columns. So this is, and most of the programs respect this. And of course, based on that structure similarity, we can interpret many things, as we will see in the coming slides. The second is evolutionary similarity, and also in this case we would like to see columns and nucleotides which is conserved and the same position. This means that they have similar function, and this may indicate some evolutionary similarity between different species or something like this. The third criteria is a functional similarity, and of course amino acids or nucleotides with the same function are in the same column. That's what we're looking for, and this means that nucleotides or amino acids which has very important function, usually very hard to mutate, and always will be in the same position. Number 4 is sequence similarity, and as we say always that most of the program, when the sequence are closely related, their structure, evolutionary, and functional similarity are equivalent to sequence similarity. So simply, if all your sequences that you have already gathered are closely related, you can find that all the 4 criteria are exist in your sequences. So main application for multiple sequence alignment. We have many applications. One of them is extrapolation. And extrapolation means that you can convince you that uncharacterized sequence is really a member of a protein family. So if you have a sequence which is uncharacterized, so we would like to confirm that this sequence is a part of a large protein family. So this simply, there is many programs that can do that with your sequence. So you can gather your sequence, use program like ExPASy plus, like this one, and of course you can see that your sequence is belong or not belong to this protein family. So this is the number 1 application, extrapolation. The number 2 is phylogenetic analysis, and also this is to reconstruct, of course, history of proteins or whatever. So you have sequences and you would like to see the relation between this sequence, the phylogenetic relation between this sequence. Another thing is pattern identification. By discovering very conserved position, you can of course identify a region that a characteristic of a function, and that's very important. And you can do that to extract some pattern by using some programs like WebLogo. As you see here, you can use WebLogo server to put your sequence, and it will do the rest. It will show you the places where sequences are conserved, and of course and pattern that you can extract from your sequence. Also domain identification, this is very important, and we have ProCite. This is a very good program to extract some domains, and you can see if you have a family of a protein, you can extract what is a domain within this family. So you can have a group of protein sequences and just put it in the program, and the program will lead you to extract the domain in your sequence. Also, one of the main applications is to find a DNA regulatory element, and there are many programs to do this, like Gibbs sampler, and there is a link here you can see and follow that. And of course, this is very good and important application too. Structure prediction, this is very important also, because the people who are interested to work with building 3D structure model and to see how things are going within that 3D structure. So for that you need also to build a multiple sequence alignment, identify some important features in your protein, and based on that you can build your model by doing this. NSP analysis, or what we call synonymous single nucleotide polymorphism, and this very important because you can from your multiple sequence alignment, you can see the single nucleotide polymorphism within your sequences. So this is a very good way of comparison and detection of this kind of SNPs. And there is a program called SIFT, and this program can be easily used to detect what you are looking for. One of the good also application is the PCR analysis. PCR analysis, you can design primers from degenerated portion of your protein family, less degenerated portion of your protein family. So the most conserved part of your family that you can design primers and isolate to fish out, in order to fish out new members by PCR, of course. And so you can just, as we said before, you can just gather your sequence and paste it in the place here in the box, which is shown here, and then you can design your degenerate primer by this program, and many people use it in this application, of course. Now we have seen now that there is many application, and but we have to consider something that is very important to understand, that the places which is important amino acid or nucleotides are not allowed to mutate. So it's the most conserved part in your multiple sequence alignment is the sequences that are not mutate. So that's why this is the most important part in your sequence. So usually you can see that the domains, the active sites in your proteins are the places that is the most conserved places, the most conserved sequences. And the places and sequences which is less important usually can be mutated easily, and that's why you can see that there is it's less conserved. So this is something we have to keep always in mind. Places that important, conserved region, are very important region. Usually it has features. And places which is less conserved or easily to change usually have not have very important features. Tips for naming sequences: you never use white spaces, don't use special symbols, never use names longer than 15 characteristics, and never give the same name to different sequences, because all these usually may have make problem in your alignment, usually make problem in a lot of programs. So that's why you have to keep this in your mind while naming your sequences. Tips for difficult MASA to interpret: of course, you can remove insertion deletion places, you can redo MAS with smaller set, you can keep trimming to interpret. Point 1 and 2, some programs can help you in this, and of course you have to keep seeing the problem in your sequence and try to, with your experience, you can remove places that you feel that it makes problem in the alignment, and by removing these pieces your alignment will be much better. This includes removing gaps, removing extremities, keeping informative blocks. This all enhancing your alignment, of course. In your own time, you can do some practical. Simply, you can isolate or retrieve some protein sequences. I suggest here heat shock factor 1. The heat shock factor 1, you can go to ExPASy.org and you can just search for heat shock factor 1 HSF1. This will lead you to different databases, and you can go to UniProt KB, and from this UniProt you can extract some sequences, protein sequences, in FASTA format, of course, and try to practice that in your own time, and before going to the next lecture. If you don't have time, go to the next lecture, and then we will see other practicals. Thank you very much.